Welcome to The Explainer. Today, we're tackling something you probably think belongs in a lab with people in white coats, the scientific method. But what if I told you it's actually one of the most powerful tools you can use for clearer thinking, in your everyday life? So let's break down this powerful toolkit for thinking.
First things first, a little question for you. Do you think you're pretty objective? That you see the world as it really is? Well, the tough truth is, our brains are kind of buggy. They're wired with some serious flaws that can really get in the way of seeing things clearly.
And this right here, this is the biggest bug in the system. It's called confirmation bias, and it's basically our brain's default setting. We just love information that confirms what we already believe, and at the same time, we get really good at ignoring or dismissing or just flat out forgetting anything that might challenge us. It's why we tend to watch certain news channels and avoid others, right? This is the fundamental problem that the scientific method was built to solve.
So how do we fight back against our own brains? How do we get around these built-in mental shortcuts? Well, that's where the scientist's toolkit comes in. The scientific method is a system, a process, designed specifically to put the brakes on our flawed intuitions and force us to think a little harder. And you can really see the difference when you put them side by side. Our everyday thinking is intuitive. It's based on gut feelings, what feels right. Our observations are casual, random, uncontrolled. But scientific thinking, that's totally different. It demands an empirical approach, which is just a fancy way of saying it's based on direct observation and experimentation. And the observation isn't casual, it's systematic, and this is the most important part, it's controlled. That precision is absolutely key. See, to study something scientifically, you can't be fuzzy about it. Scientists use this word construct to talk about the big ideas they study, things like intelligence or depression or aggression. The very first step is to get super clear and define exactly what it is you're talking about. And the tool they use for this is just brilliant. It's called an operational definition. So instead of a vague idea like intelligence, a scientist using an operational definition might say, intelligence is the score you get on this specific IQ test. See what that does? It takes it from a feeling to a number. It's not about what seems right. It's about what we can all observe and measure. That way, everyone is working from the same playbook.
Okay, but just because you're measuring something doesn't mean you're doing it right. Any good measurement has to pass two huge tests. First up is validity. Is it truthful? Is your IQ test actually measuring intelligence, or is it just measuring how good you are at taking tests? And second is reliability. Is it consistent? If you took that same test next week, would you get a pretty similar score? For a measurement to be worth anything, you have to have both. All right, so these ideas can feel a little abstract. Let's make it real. We're going to see this whole toolkit in action by looking at a true story, a puzzle that totally stumped everyone over 100 years ago. Let me tell you about a horse named Clever Hans. So, Clever Hans was a total superstar. His owner, a German math teacher, claimed this horse could solve math problems, tell you the time, even read, all by tapping his hoof. And here's the crazy part. Hans could still do it even when his owner wasn't the one asking the questions. For pretty much everyone who saw it, it looked like straight-up magic, a genius horse. But, scientists aren't really satisfied with how things look. They knew the secret to cracking this mystery boiled down to one single essential ingredient: control. The real difference between just kind of watching something happen and actually doing science is taking control of the situation so you can isolate what's really going on. And that is exactly what they did. Just look at how systematic this is. Okay, first condition. The person asking the question knows the answer. And boom, Hans is a genius, gets it right. But then they changed one simple thing. Test condition 2. The questioner doesn't know the answer. And suddenly, Hans failed. Every single time. And just to be sure, test 3. They put blinders on Hans so he couldn't see the person asking. Again, he failed. It turns out Hans was a genius, just not at math. He was a master at observing people, picking up on tiny unintentional cues, a raised eyebrow, a slight lean forward, from the humans who knew the right answer. It was the controlled observation that finally revealed the truth.
So the story of Clever Hans is just a perfect example of how science works. Now let's talk about the what. What are we actually trying to do when we use this toolkit? Turns out there are 4 main goals.
And these goals really build on each other. It all starts with description, just carefully observing and classifying what's going on. Once you've done that enough, you can move to prediction. You start to see that two things often happen together, so you can predict one from the other. But the third goal, explanation, that's the tough one. That's about figuring out the actual cause. And once you have that, you get to the final goal, application, using that knowledge to actually improve people's lives. Let's zero in on that third goal for a minute because it's easily the most powerful and also the hardest to get to. Explanation isn't just about knowing what happens, it's about understanding why it happens. This is the search for cause and effect. And right here is where almost all of us get tripped up in daily life. You need to burn this into your brain. Correlation is not causation. Just because two things happen together, our brain wants to draw a straight line and say A causes B. But think about it. Ice cream sales go up in the summer, and so do shark attacks. That doesn't mean buying a scoop of vanilla is going to get you bitten, right? There's something else going on. To actually prove that one thing causes another, scientists have to clear three incredibly high hurdles. First, the two things have to co-vary. When one changes, the other one has to change too. Makes sense. Second, the cause has to happen before the effect. Also makes sense. But it's this third one that's the real killer. You have to eliminate every other possible cause. And the reason that third step is so tough is because of this problem called confounding. This is what happens when some other variable gets tangled up with the one you're trying to study. So imagine you're testing a new teaching method. You use it on a morning class and use the old method on an afternoon class. The morning class does way better. Was it your new method, or was it because they were fresh in the morning? You don't know. The variables are confounded, and your whole experiment is basically useless. So, we've gone through a lot here. What's the big picture? What's the main takeaway? Well, it's that this whole thing isn't just for researchers. It's about developing a whole new mindset. At the end of the day, the scientific method isn't some boring list of rules you have to follow in a lab. It's really just a structured way of being curious. It's a commitment to being a little skeptical, to defining what you're talking about, to checking for your own biases, and to demanding really good evidence before you jump to conclusions about why something is happening. And that brings us to one last thought for you to take with you. Think about some common fact that you believe, something that everybody just knows is true. Now, how would you put it to the test using this toolkit? What's the concept? How would you define it so you could measure it? And maybe most importantly, what other possible explanations have you maybe never even considered?